Hi everyone. In this video we're going to build on our knowledge of graphing lines to talk about graphing linear inequalities. So we'll look at examples with just a single inequality as well as systems of inequalities and a couple word problems where we can write linear inequalities first and then make the graphs. So here's example 1. Okay, and this is a system of linear inequalities. So we have two of them, okay, just like a system of linear equations. And notice for inequalities, instead of equal signs, we now have these symbols. Okay, we have greater than or less than symbols, we have less than or equal to symbols, and we have greater than or equal to symbols. Before we get to the procedure, let's talk a little bit about what these graphs will look like. All right. Okay, if we looked at a graph really quickly, let's look at an example like x is greater than or equal to 4. What would that graph look like? So if I think about points that make this inequality true, first of all, I know that any points where x actually equals 4 are going to work. So like 4, 0, 4, 1, okay, 4, negative 2, things like that. And since x is greater than or equal to 4, I know that any points where x is greater than 4 will also work. So I could do things like 5, 0, 5, 3.3. It doesn't really matter what y is. Okay, things like 15, okay, square root 3, things like that. All of these points will work. So if you've seen these before, you may remember that when we go to graph this, let me slide this over. Okay, so let me go to make my graph here. So here is, let's see, we'll go 1, 2, 3, 4. Here's x equals 4, and all of these points. Okay, so I have 4, 0, 4, 1, 4, negative 2. All of the fractions in between those, they're all going to work. So like 4.5. All right, and basically all of these points up and down, okay, where x equals 4. So I end up with a straight line. That's part of the graph. Okay, and then anything that has a coordinate, an x coordinate greater than or equal to 4 also works. So where are those coordinates? Well, if I look at the number line, here's 5, here's 6, here's 7. All right, and y can be anything, but basically it's all of these points. Okay, and also the fractions, like 4.5 is okay. All right, so basically what I end up with is a coordinate plane that's been divided into two regions, okay, by this inequality. Okay, so if it was just x equals 4, that's kind of this dividing boundary line. And then I end up with half of the coordinate plane shaded, either one side or the other of that line. So all inequalities look like this. There's going to be some sort of a boundary line and then shading to one side or the other. Okay. Now what do we do if it was something like x is greater than 4, not equal to? Well, then I'd have to throw out some of these points. I couldn't use any points where x is a 4, but I want to show that my points can go really, really close to that. Like I can go up to, like 4.0011, that's okay. So how do I show that I can get really close to that line, this line, but not actually equal to it? Well, you may remember we do a dotted line to show that it's right up to that line. Okay, so here's a summary of the procedure for graphing a linear inequality. We temporarily replace the inequality symbol with an equal sign and graph that line. This is called the boundary line. Okay, so we use a dashed line if it's either a less than symbol or a greater than symbol, a strict inequality. Use a solid line if it's less than or equal to or greater than or equal to. Okay, that indicates that the points on the line are included in the solution. Then to decide which half of the plane to shade, we pick a point not on the line and use it as like a test point. So we substitute the coordinates into the inequality to see if the resulting statement is true or false. Right? If the test point makes the inequality true, we shade the side that contains that point, and if the test point makes the inequality false, then we shade the other side. And that shaded region is the solution set of the inequality. That shows all of the points that make the inequality true. Alright, so we'll review these steps as we work through some examples. Here's example 1. Graph x minus y is greater than or equal to 6. So first of all, ignore the inequality symbol and just pretend that it's an equal sign and graph that line. So you have your couple options. You can use y equals mx plus b, or you could use the intercepts, or really any points that you like. So if we did intercepts here, the point 6, 0 would work, and the point 0, negative 6 would work. Okay, or slope-intercept form, subtract x, and get negative y equals negative x plus 6, and then divide by negative 1, y equals x minus 6. Alright, so there are the two options. So either way, here's what I end up with. Okay, here's negative 6, here's positive 6. Alright, and if I used slope, let's see, I'd be going like up 1 over 1, and eventually I'd end up with the same thing. Alright, so let me connect these with a line, and let me try to get this with the right slope, and that's pretty close. Alright, is this dotted or solid? Well, it's a greater than or equal to sign, so this is a solid line, so I can leave that. And then to decide which side of the line to shade, okay, I'm going to use a test point. I like 0, 0. This will work every time as long as it's not on the line itself. So you always want to choose a line either on the left side of the line or the right or above or below, just not actually on the line itself. So I'm going to choose 0, 0 as the test point. I'm going to substitute that point into the inequality. So now I'm back to the one with the inequality symbol, not the equal sign. And I'm going to see if this is true or false. So I end up with 0 is greater than or equal to 6, and that is false. So I don't want to shade the 0, 0 side. I want to shade the other side of the line, and that's this region here. Okay, so that is the solution set. So now I won't do this every time, but let's check a few of those points just to make sure that that is correct. So first of all, if I pick out a point on the line, I'll pick this one, and this is the point 8, 2. So let me plug that in and make sure that that works. 8 minus 2 is greater than or equal to 6. 6 is greater than or equal to 6, and that is true. Any point on the line, you should end up with the same number on both sides. Okay, so that's the equal to part of that symbol. Let me choose another point in the shaded region. So I'll choose, how about 2, this is 2, negative 5. And I want to make sure that that makes the inequality true. So 2 minus negative 5 is greater than or equal to 6. Okay, so 2 minus negative 5 is 7, and that is true. All right, and then one more, let me test a point that's not in the shaded region. How about 4, 1? Let me make sure that this, okay, I want to make sure that that does not make the equation true. Okay, so 4, 1, we plug that in, and I end up with 3 is greater than or equal to 6, which is false. just as we expected and wanted it to be. All right, example 2, graph 2x plus 4y is less than 12. All right, so I might do intercepts for this one as well. If x is 0, then I have, okay, so I have 2x plus 4y. I'm pretending that this is equal to 12. If x is 0, then I end up with 4y equals 12, and so y would equal 3. Okay, so I have the point 0, 3. And then if I have y equal to 0, okay, then I can solve for x and find that x is 6. So there are my 2 points. Okay, so here's 6, 0, and then 0, 3. This one, dotted or solid, well, this is a less than symbol, so I want to show that all of the points where 2x plus 4y equals 12 on the boundary line, I want to show that those are not actually included in the solution. So I want to use a dotted line here. And I might just do a few other points. This slope is like down 3 over 6. And I can do things that are equivalent to that. So down 3 over 6 is also like down 1 over 3. Okay, so let me go, I'll find a few other points on this line. Okay, so I'm going to go down 1 over 3. Oops. Okay, or I could go up 1, back 3. And here's a few more. And by the time I've sketched those in, oops. Oh, that's not correct. Down 1 over 2, sorry. Okay, that's a little better. And then I'm just going to connect these with a dotted line. I pretty much almost have a dotted line at that point. All right, how about the shading? Well, 0, 0 is not on the line, so I'm going to stick with that as the test point. Okay, so I'd have 2 times 0 plus 4 times 0 is less than 12. And I end up with 0 is less than 12. That is a true statement. So I do want to shade the side of the line that has 0, 0. So that's over here. And that's the solution. Okay. Example 3, solve the system graphically. So in this case, solve, okay, because all of the solutions are shading, what I mean here is which points, or which shaded region is going to work to make both of those equations, or in this case inequalities, both inequalities true. So what I'm looking for is, I'll have 2 lines, one here's dotted, one is solid. Okay, they're each going to have their own shading, but there's going to be a part where the shading overlaps, and that's going to be the solution to the system of inequalities. Okay, so we start by just graphing them individually. So x plus 3y is greater than or equal to 6. I'll use intercepts again. Okay, I'm going to have 6, 0, and 0, 2. Alright, and for this one, I will have 5, 0, and 0, negative 10. Okay, so 6, 0, and 0, 2. This top line, this is a solid line because it's a greater than or equal to symbol. Okay, and this one is, yeah, this is the slope of negative 1/3, down 1 over 3. So I'll fill in a few more points here. Okay, there we go. The second one, 5, 0, and 0, negative 10. And that line, there's that one. Now this one is a less than symbol, so this is a dotted line. So let me go back and erase a little bit. Make this dotted. Oops, it's too much. Okay, that's better. Alright, so dotted line. And then I need to worry about shading for these lines. Okay, so the first line, if I do 0, 0 as a test point, I end up with 0 is greater than or equal to 6. That's false. So I'm going to shade above, away from the 0, 0 on that line. And then for the, I'll fill that in. Okay, and then the second one that I did, I end up with 0 is less than 10. That's true. So I am going to shade the 0, 0 side for that line. And just ignore the other line when you're shading either of these. So I'm ignoring the green line, just shading right over it with the blue. Okay. And then I look at where the shading overlaps. So here is this region. Okay, it goes along here, and then it follows like a dotted line here. All right, and then anything in here is a solution. So sometimes what we'll do is, sometimes we'll do the overlapped shading, or sometimes we might just mark this with an S for the solution set. Okay, or you could circle it or anything you want to do to show that that shaded overlapped part is where the solutions to the inequality are. Now let's talk about naming some points that are solutions. So I can choose anything in that region. Okay, I can choose like this point. I can actually choose anything on the green line. That's going to be okay because all of those points are included. I can't choose anything on the dotted line because those points are not included. All right. So if you try it out, like these points here, they're going to fit with the green shading, but they're not going to work for the blue inequality. All right. So let's try one of them just to emphasize that. So like I'll pick out this intercept. I know this one. Okay. I don't see any obvious ones here. Let's see. Actually, I think this is -10. This is a 5, so I think my slope, it looks like I'm going up 10 over 5. So that's a slope of 2, so I think I can pick out one of these points. This is the point 6, 2. And I know for sure that that's on the boundary line. So notice if I plug that into each of these equations, okay, or inequalities. So the first one, 6 plus 3 times 2 is greater than or equal to 6. So that's 6 plus 6 is 12. And that checks out. That is a true statement. Okay, so this red point, this one, okay, that fits in with the green shading into that inequality. Now when I substitute it into the blue one, so 2 times this one, 2 times 6 minus 2 is less than 10. Okay, I get 12 minus 2 is 10. 10 is less than 10. That is false. Okay, it doesn't have that little equal to part under it. Alright, so that's not part of the solution. Okay, what about x is greater than -3, y is less than or equal to 10? Alright, well, these are horizontal and vertical boundary lines, and we've already graphed things like x equals -3, and we've already graphed things like y equals 10, so I need to do that and then just look at the shading. Alright, so x equals -3. I want to go on the x-axis to where x is -3. And since this is greater than, this is a dotted line, so I'm going to draw a vertical dotted line through that point. Alright, how about shading? I can still use 0, 0 as a test point. I'm just going to plug half of it in because I don't really care what y is in this inequality. So I substitute 0 for x. 0 is greater than or equal to negative 3. Or I'm sorry, 0 is greater than negative 3. That is true, so I'm going to shade that side of the boundary line. The second one, y is less than or equal to 10. Well, here's y equals 10. Okay, it's a solid line since it's less than or equal to. And then a test point, if I plug in 0, 0 is less than or equal to 10, that's true. All right, or basically this is saying shade all of the points that have y coordinates less than or equal to 10. And if you think of this as the y-axis as a number line, okay, then you can see visually where all of those points would be. So we're shading all of these points below. So the solution set is this region in here. Okay, I can pick out any points in the region. I can pick out any points along this blue line. I can't pick any points along the red dotted line. Okay, don't choose those. All right, we will stop there, and then in the next video I will look at the next two examples, and we will write some inequalities from word problems.